Hello everyone. In this video we are going to talk about one of the topics that is typically not taught during elementary dynamics courses in undergrad, and that is called the rolling resistance. Some people call it also rolling friction. I would rather call it resistance because the mechanism of it is a little bit different than the Coulombic friction I mentioned in one of my previous videos, so I would rather call it rolling resistance. But the effect of it is similar to friction. It acts basically opposite to the direction of motion, and it basically converts your mechanical energy into heat, into sound, and it's a non-conservative force. So one of the examples that comes to your mind is if I have a rolling disc, a tire, any object, and I give it some initial velocity or some initial rotation, okay? So here it has some omega 1 non-zero, and it starts rolling without slipping and goes from position 1 to position 2. So again, here it is rolling without slipping. So there is no kinetic friction to change the mechanical energy. Then you would see after some distance, whatever it is, depends on the conditions we are going to discuss in a bit, you will see ultimately it would stop. It doesn't roll forever, and as long as this road is flat and it is not really inclined, when the road is completely flat, you see ultimately it would stop, correct? So what you will see is it goes to omega 2 equals 0, and so the velocity of the center of mass is also V2 is going to be equal to R times omega 2. Is going to be 0 here. The velocity of the center, V1, is equal to R times omega 1, and it is non-zero. So here, kinetic energy in position 1, K1, is basically bigger than 0, while here, kinetic energy 2 is equal to 0. And R, when we say R here, by R means the radius of the disk. So now the question is, if I assume here the datum for gravity is at the center of the disk, so then I can say that potential energy in position 1 is 0, potential 1 in position 2 is 0. And as I said, K1, which is equal to 1/2 I about the center omega 1 squared plus 1/2 m times V of the center at position 1 squared, where V of the center is this point, and m is the mass of this guy. So clearly it's bigger than 0, while in position 2 is 0. And so if I write my work energy equation, which says total work done between position 1 and 2 is equal to K2 minus K1. Well, if you draw the free body diagram, the only two forces acting on this object are gravity and normal force, even if there is static friction in the beginning, okay? Even if in the beginning to start rolling, if you give it a velocity and then it starts catching the rolling, even this static friction Fs is not going to do any work, because it is applied to a stationary point, the contact point. And N and Mg are both also perpendicular to the direction of motion, so there is no work. The total work is 0. While K2 is 0, K1 is bigger than 0, so the left-hand side is going to be negative, which means you lost kinetic energy, but the right-hand side. But the left-hand side is 0, and this cannot be, right? That 0 is equal to some negative number. So you see, it looks like your principle of work energy is violated here. And we say, well, it doesn't work, right? Unless there is something that does some negative work So it justifies this reduction in kinetic energy. And what is that? That's what we call the rolling resistance. So as we're going to see in a minute, the rolling resistance is basically a force that acts quite similar to the friction, if I call it the force of rolling resistance. And that force, it is going to do a negative work. Okay, you can show that that force can be considered as CRR, a coefficient we call coefficient of rolling resistance, times N. And it's not like it's just applied to this stationary point, so it is going to do some negative work. So the work of this is going to be negative CRR, the coefficient, times N times delta S, where delta S is this distance traveled. Okay, and now this is negative, and it can justify this reduction in kinetic energy. But what is this rolling resistance? Where does it come from? And how do we characterize it? What is the CRR and so on? So let's talk about that. So if we look at the example of a tire here, you know, anytime you roll a tire on a flat surface, it would stop. Why is that? So if you look at the tire here as it is moving in the car, and that's one of the reasons when you are driving on the road, correct? If you remove your foot from the top of the accelerator, you see your car will stop what? Reducing the speed. Now a portion of it is due to the air drag, okay? But that's not all of it. Even if you moved in somewhere with very low air pressure, even if you drive in vacuum, you still would see that your car is going to slow down. Why is it? As I said, it's because of this rolling resistance. Now, what is that? For pneumatic tires with rubber material filled with air, the rubber, as you know, has something we call hysteresis. What is that? So if you apply a tensile load on the rubber and make it stretch, and you plot the stress versus strain diagram, you see that the plot of the stress versus strain is basically this solid curve here. You're starting from 0 for 0 displacement, and then after a little bit it goes from elastic to plastic behavior. And now the thing is, if you remove the load and start compressing it, or unload it, or maybe, as I said, even compress it, for compressed the stress has to be negative, so here is mostly unloading. If you remove the load, it's not going to come back on the same curve it went up. It's not going to go back on the same curve back to the 0, 0 stress and strain. What it does, it goes under a different path. So the loading and unloading curves are different, and there is an area between them which corresponds to, as you know, the area under the stress strain curve is energy, correct? This is energy per volume. So here is an energy that is lost. Okay, because here you are applying some energy, but it is not giving you back the whole thing. It is storing a little bit of it and converting it into sound and heat. So the area inside here, and this phenomenon, as I said, that the loading and unloading curves are different, and there is a area between them, we call it hysteresis. And this here, this area, it corresponds to the energy loss. And by loss, I mean converting it into other forms of energy like sound and heat that you cannot easily get back into original kinetic energy due to increase in entropy. So this hysteresis is one way that you can justify the loss of energy in pneumatic tires. Now, where does that happen? So if you look here as on the picture of a tire in motion, You see that, so this tire is going like that. And when this red patch comes into contact with the ground, if you look at the length of it is definitely shrinked, right? So the length of the red patch is way bigger than the blue patch. You can easily visualize that. And that means a compression. So when it comes into the contact, here we call it the contact patch, you are going to have a compression, and then when it goes back, again, the compression is released because the weight of the car is not on that contact patch anymore, and so you have unloading. So from here to here, this is loading, and from here to here, it is unloading. And during this process is where you lose some energy. You're going to hear sound, correct? And depending on the condition of the tire and condition of the road, you clearly always hear the sound under the tires and some heat. Okay, so that is corresponding to this area within this hysteresis loop. And that is one way you can basically explain the loss in energy. There are a couple of other ways that you can explain that. One other way is this. When two objects are in contact, the matter of fact is none of these two objects are completely solid. There is no perfectly solid object in the nature. And of course, the smoother the road is, right? So the material is not as stiff, or there is summer that there is a lot of heat and the pavement, the asphalt or something goes a little bit soft. If you look clearly, because of the weight of the car, you will see that this tire will penetrate a little bit into the surface of the road, and so here you have deformation. And the thing is, it's actually a little bit, if you look on microscopic level, it is not even as flat and nice as this, and it's not just this area that you deform. What you will create is actually like a wave, a little bit in the vicinity of the tire. And the total normal reaction from these areas is not going to be vertical. It is going to be at angle, and so it has two components. A vertical component, N, that you always know, and that will cancel your weight, and it has this X component, Rx, which the same as what for us? That rolling force. So let me call it just F of the rolling resistance. And this one is clearly acting opposite to the direction of motion and is wasting energy. Okay? And so the real life dynamics of a tire is more than the contact is one single point. No. The matter of fact is the contact between the tire and the road happens in more than a single point. It actually happens over an area which we call the contact patch. So you have an area of contact, not just a line of contact. And when the horizontal component in the opposite direction of the motion is applied to many of these contact points, they will create a negative work component that will reduce your kinetic energy over time. Okay, and again, as I said, if you look here, maybe it's not as easy to understand why it is backwards a little bit, but if you look at, as I said, the wave type of shape of this surface, which is more realistic, if you look here at this point, there is contact, there is tangency between, so it might not be as perfect as this, it might be actually something like, let me show you. Might be something like this. As I said, there are some waves. It's not just as perfect and pure like that. And here you definitely have a contact, and if you look at the tangent line here and the normal line is clearly tilted backwards. Okay, so that's another way that you can explain why there is a backward force from the contact, and that is doing a negative work. And finally, another way, if you want to basically explain this rolling resistance, is the distribution of pressure on the contact patch. So if you look at the contact patch and if you plot the pressure, which is the normal force per area, over the contact patch, it's not uniform, okay? And the distribution of that is non-uniform. So here the tire is moving like this. It is going clockwise, it is moving forward. And in this area where the rubber comes into contact with the ground first, you have a little bit higher pressure than in the back area where the patch is released and is unloaded. And so if you find the resultant force of this whole pressure distribution, the resultant force, which here is shown by this big arrow, is not going to completely pass through the center of the tire. So there is a little bit of offset here, okay, this much. And if you call this force N, and if you call this distance T, then from this T and N created a, so this is the ta of the engine, T of the engine or the gearbox. This is the T of the rolling resistance, which is equal to N times D. You clearly see this torque is going to oppose the torque applied to the driving tires, and that's another way you can justify the waste in energy, right? It's an opposite torque. So whether you call it opposite torque, you call it opposite force, or you call it hysteresis, the matter of fact is when an object rolls on the floor of any type, there is always a resistance backwards which wastes the kinetic energy. Now, for example, if you have this pneumatic tires, for pneumatic tires, the hysteresis is the big thing because the loading and unloading curves are not on the top of each other. But you might say, well, it's not just the pneumatic tires when you roll them that they stop. If I have a wheel made of steel, and that wheel that is made of steel is rolled on even a ground that is very hard, let's say the ground is also made of steel like the railroad, correct? The wheels of the train on the railroad, you still have what? You still have the rolling resistance, while for the steel, this loading and unloading, as long as the deformation is not huge, is quite on the top of each other. Unless, as I said, you go into plastic region for the steel, and then yes, also there you will have permanent deformation and you have strain energy that is wasted. But mostly for railroads and the wheels of the trains, you really do not go to the plastic region. You never see a train passes the railroad and the railroad shape changes permanently. Okay, they might over a long time a little bit, but really not. It's mostly in the elastic region. And as you know, for a material like steel, once you go in the elastic region, if you unload, you go back on the same line and there is no cycle. Yes, if you go to the plastic region, you know, for the steel, for which the strain is stressed like this, if you pass the yield strength and you go to the plastic region like this, once you unload here, you're going to go back like this, parallel to the linear region. And so you will have here permanent deformation and loss in energy. We call it the strain energy. So you can justify. But for most of the applications, you only operate in the linear region. You go and unloading and unloading on the same curve. There is no loss in energy due to that. So what basically can justify the, or again, explain the rolling resistance for a steel wheel on a steel rail is really this backward component of the normal force or this opposite torque, not the hysteresis. Okay, but for pneumatic tires, it's really the combination. So it's either one of these, because these two are equivalent. Okay, you can either use this one or this one. These two are equivalent, not that they are two complementary mechanisms. No, you can either use the negative force of the backward component of the normal force or the opposite moment. So these two, and then what? Plus this hysteresis is what makes the rolling resistance. For pneumatic tire, both of them will work against you. For steel wheels on hard surfaces like steel rails, it's mostly basically this opposite force or opposite torque, which is acting because the hysteresis is not significant. Okay, so hopefully at this point you have an idea of where the rolling resistance comes from, and the amount of it and the type of it depends on the material and the contact surfaces. So now, what's the formula for calculating this rolling resistance? Well, what they came up with experimentally is a formula similar to the Coulomb friction. So remember, in the Coulomb friction, we had F to be a constant like mu times N, like Fk was mu k times N. So they said the kinetic friction is proportional to the normal N times a constant, which depends on the surfaces and some other conditions like temperature, humidity, and so on, surface roughness. So they experimentally came with something like this, FRR equals CRR times N. So they say that the rolling resistance is also proportional to the normal force. The harder you push the surfaces together with the larger force, of course, the deformation is going to be more. So this normal force N, or the horizontal component of it, is bigger. The hysteresis cycle is bigger, and you're going to have a larger rolling resistance. And then the constant of that linearity, they call it the coefficient of rolling resistance, RR. Now, this is an experimental formula, and CRR is experimentally determined for some specific types of contacts, and it has its own limitations too, and it's not perfect. It's not applicable to all sorts of conditions. But if you go and look here at this table, which I got from Wikipedia, so for example, it says CRR for pure rolling resistance of railroad steel wheel on steel rail. The number, as you can see, is quite small, okay? 3 or 4 over 10,000. So it's not a big number because the surfaces are hard, so deformations are small, there is no hysteresis, so there is not too much of rolling resistance. Okay, so you can bring the numbers down. But if you have, for example, what? If you have, let's go down a little bit in the list and look at some bigger numbers. Ordinary car tires on sand. Of course, you don't want to ride your tire on sand, but if you do, you know you are going to get loss of resistance, right? If you roll something on sand, it is going to stop shortly. For ordinary cars on concrete, which is for many of our roads, you're looking at 0.01 to 0.015, and it depends on so many conditions. Okay, so for large truck tires, semis, it is 0.004 to 0.008. Okay, so you see probably for regular cars on concrete, you have bigger numbers than the semis. Why? Because the diameter is big, and we'll talk about it. But there are some of these numbers experimentally calculated. They are not perfect. They are just for some controlled conditions. And for each condition, if you really want it, you have to calculate it yourself or just approximate. So what are the factors that affect the value of this rolling resistance coefficient or the whole force, CRR or FRR? What are they? One is material. Of course, if the material is more flexible and under load, it deforms more, you will have more of the hysteresis cycle for especially many of types of material like rubber, and you will have a higher chance of large rolling resistance values. Dimensions. It says if you have two tires with the same amount of inflation pressure, the one that has wider tires will have lower rolling resistance. Okay, because that pressure is the pressure due to the weight of the car or bicycle or whatever it is going to be applied over a wider contact patch, and the pressure distribution is going to be a little bit closer to uniform normal, and so that d distance that we talked about here is going to be smaller. This total force is going to be closer to the bottom of the center. Okay, so it will be something a little bit like this, which brings this guy a little bit more toward the center. And also the amount of penetration will be smaller because the overall pressure is lower. You have a bigger contact area, so the pressure is lower. So instead of this much of penetration here, you might only have this much of penetration. Okay, so a wider contact area, wider tracks means really lower resistance. The amount of inflation, of course, if you have lower pressure in the tires, it means higher rolling resistance, and you probably all experienced it, right? If your car tires are not well inflated, for example, instead of 35 psi or 36, they are at 30, 29, 31 or so, you see that over time you are burning a lot more gas, correct? So that's why they say if you want to reduce the amount of gas consumption in your car, make sure that the pressure in your tires is well high enough, because if it's not, then they will deform a lot more under the weight of the car, and there will be more hysteresis and there will be more waste of the energy. Then we have tire thread thickness and shape. So if the threads are thicker and they are more contoured instead of simpler and narrower, then you will have bigger, higher resistance because they can penetrate more. Diameter. For pneumatic tires, the diameter is negligible. Not that it's zero, it's not as much as when you have steel wheel on hard rails. For steel wheel on hard rails, you can show that it's inversely proportional to the square root of the wheel. So FRR is proportional to 1 over square root of D, where D is the diameter of the wheel. So the bigger the wheel, the smaller the rolling resistance is going to be. Like if you make the wheels 4 times bigger, you are going to have 2 times smaller rolling resistance. For pneumatic tires, it's not as significant. Still, if you make D a little bit bigger, your FR is not going to be as obvious as this, but you will still get some reduction, and that's what you saw that semis have a little bit smaller CRR compared to ordinary cars. Of course, here it doesn't say whether it's concrete or not, but they have a little bit less. The thing is, they have more load on them. So the comparison has to be only with one factor changing and not everything else. So that's a little bit hard to compare based on just those two numbers. Temperature, of course. The rolling resistance is going to go down when the temperature is going to go up, and probably because it will make the pressure in the tires go up. Now, this is on the aspect of the tire. This is not completely true. It depends. Like if it's concrete, if the road is concrete, probably yes. When the temperature goes up, the pressure in the tire goes up, and you get lower rolling resistance. But if the road is made of asphalt or something that's softened due to the increase in temperature, you are going to get more rolling resistance. So this is not like a general rule. It depends on what kind of road you are talking about. Applied torque. It says if you apply a lot of torque on the driving wheel, your rolling resistance would go up, of course, because you're applying lots of torque. Lots of torque means this pressure distribution will be larger, and you need a lot more pressure to create the amount of traction you need to move the car. And you're using the max, basically, friction from the surface to generate the traction for you. And that means you're deforming the surface a little bit more, so that normal force is going to be more, and you will get more rolling resistance. And finally, the curvature of the road, which says if the road is curved, it has more rolling resistance, right? So if you're driving on a road like this, you will probably get what? More rolling resistance than somebody who is driving on a flat road, right? And again, because here you have a higher chance of deforming the surface of the road, okay? Because here it's just the weight, but here, if you look, your mg is like that, and it has two components, and you might say, well, here it looks like less because this n component is going to be like mg cosine of alpha if this angle is alpha, the angle of the tangent line. So a smaller number is applied to the road, yes, but you have to look at the actual distribution of the load, because what you're looking here is just a simple explanation. What you have really is, if you have a system like this, you have two normal forces here and here. And when you're going on the hill, the distribution of the load on the two tires, if we call it N1 and N2 here, the difference between N1 and N2 is depending on the weight distribution in the car, okay, depending on where the engine is and everything. But here, the fact that N1 has to provide rotational stability so the car does not flip back, N1 is going to increase more significantly compared to here. So if the difference here between N1 and N2 is, let's say, 200 units, here it might be 500 units if N1 is bigger, for example. And that means here you have more pressure on these driven tires. And here also you have to apply more torque to lift the weight of the car over the slope. And you know, more torque means more rolling resistance. Okay, so this curvature of the road, the reason that it makes more rolling resistance is because of those two factors. So hopefully I could tell you a little bit about where the rolling resistance comes from, what's the effect of it, what's the formula for it, some sample numbers and important factors affecting it. As I said, this is typically not discussed in undergrad dynamics, and that's why somebody can easily give you a hard time by saying, hey, this object, I give it some velocity, it goes to rest. Based on the work energy equation, the two sides are not equal, so does it mean that the work energy principle is wrong? No, you are not just considering one of the forces acting on the object. Okay, now that you know it, you can easily justify that why it is stopping. Okay, thanks for your attention. See you in the next video.